and the thing that we need to do Nakayama's lemma is the Cayley-Hamilton theorem. So that's what's right here. So it says essentially that if you have an endomorphism of a finitely generated R module, right, then there is a polynomial, right, which annihilates the module, right? Moreover, it can be arranged in such a, okay, so one of the things that you can do is if you add the additional hypothesis that the image of M is in IM, so an ideal times M, then the coefficients of the polynomial that you get, this kind of characteristic polynomial, which depends on your choice of generators, but the characteristic polynomial, you can arrange so that the coefficients are in appropriate powers of the ideal. Okay? So, yeah. So that's all I wanted to say about that. And we're gonna use this at the very beginning. All right. So what I'm gonna do is I'm gonna do Nakayama's lemma. Oh.
Can I ask a quick question about?
Yeah.
So it's sort of the characteristic polynomial is only for a square matrix, but invariant factors could be for any. Doesn't a matrix associated to a module representation wouldn't necessarily have to be square, right? And the invariant factors
It has
could
to be square because you need to have an endomorphism. So okay, so for modules over Pi, so if you're looking at endomorphism of a vector space, right?
Yeah.
Then it has to go from the vector space to itself, which means the dimension of the domain and the dimension of the codomain need to be the same. So that makes it a square matrix.
Okay.
Yeah. Yeah. But the invariant factor stuff applies to all modules over PIDs. So.
Right. Okay. Cool.
Yeah.
Thank you.
Okay. So Nakayama's lemma. So like I said, I'm going to give 3 versions of this thing. Okay, and it's going to rely on the Cayley-Hamilton theorem. So you guys can look in the notes and scroll back here. So the link to this is from the previous class. Okay, so the theorem is the following. Or let's say version 1. Of Nakayama. Okay, so it's all about finitely generated modules. So let M be a finitely generated module over a ring R. Okay, and let I be an ideal in R. Okay, so if M is equal to IM, this implies that M is equal to RM. Okay, for some R and I. So meaning that if you know that the module is always, everything in the module can be written with coefficients in I, then there exists some R, right, that acts as multiplication by the identity. Okay, that's the first version. All right, so let's do the proof. Okay, so to do this, essentially what we're going to do is so what we'll do is we let phi be the identity of M. So be the identity automorphism of M. Okay, so by the lemma, so by Cayley-Hamilton, there's a polynomial okay, and the polynomial looks like a0 plus a1x plus ... plus an x, well, so an minus 1 x to the n plus n minus 1 plus x to the n. Let's call this p of x, such that p of phi, 1 p of phi acts as the identity, or sorry, annihilates m, and 2, so that a0 through an minus 1, these are elements of I. At least. They can be larger powers of I. Okay? So I guess this one's an I to the n. The 0 one is an I to the n. And this one is in just I. And the n here is the number of generators. So n here is the number of generators of m. So it could be a number of generators. You can always take more generators than you need if you want. But it's a number of generators of m. Okay, so we have this. Okay, so this means that, so for all m and m, right, so then p of the identity of m applied to m is equal to 0. And this thing here is, let's just write it out. So this is a0 plus a1 plus a2 plus dot 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 plus an, plus an minus 1 plus 1 times m. Okay? Because we plugged in the identity into the matrix, in for x. Okay? So that's what happens when we plug the identity in for x. Okay? And this tells us that a0, okay, so minus a0 plus a1 plus a2 plus dot 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 plus an minus 1 of m is equal to m. All right? And so this is the r. Is r from the statement of the lemma. Okay? Cool? So again, what happened is that if you have m and it's equal to im, then there's going to be some element of the ideal that acts as the identity. All right, that's the first version. All right, let's do the second version. So now this just starts to become super useful. Okay, the second version, we'll start to see applications. So here's version 2. Feel free to interrupt me with questions if you guys have any. Okay, so the hypotheses are the same. So let M be a finitely generated R module. Okay, and let I be an ideal. Okay, contained in the Jacobson radical. Okay, so what was special about the Jacobson radical? Okay, so the Jacobson radical. So let me just do a quick. Okay, let me just give the statement, and then so if the statement is if im is equal to m, this implies that m is equal to 0. Okay, so maybe I'll just say what the Jacobson radical is again. So this was the intersection of all maximal ideals. And the key point was that 1 plus j. So this was contained in R star. So these were units. Okay, that's one of the things that we have. Okay, so that's what we're using it for, to produce units. And that's where the thing where we always use this trick where you have if you have a non-unit element, then it's contained in a maximal ideal, blah, 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 blah. Okay, that's how those proofs went. All right, so let's do the proof. Okay, so by version 1 of Nakayama, right, there exists some R in I such that 1 plus R times M is equal to M for all M and M. Right, so it acted as the identity. Or let's see. Sorry, this is not what I want to say. RM. That's what we had. Okay. So this implies that 1 minus R M is equal to 0. Right, for all M. Right, but this is a unit. This is an element of 1 plus J. The Jacobson radical, so this is a unit. It's an invertible. Okay, so this implies M is equal to 0. So, multiplying on the left by the inverse of this thing, right? This implies M is equal to 0 for all M and M. So this implies M is equal to 0. Okay, so it gives us a nice criteria to determine when this is 0. Okay, so in applications, any questions about this?
You're gonna follow up and finish with that statement of like where this is useful, right? Because I was
Yeah. I'm gonna give you some examples of where this is useful, and then there's a ton of exercises on this too. Okay. Yeah. So let me give you an example. All right. So so just kind of like a remark. In a lot of applications, we check that M. Oh, where are we? M is equal to IM by checking that M mod IM is 0. And then there's a lot of like auxiliary things. So, we'll have some module and then we'll construct some other module N, and then we'll check, N mod IN is equal to 0. And we'll see this in a second. All right. Okay, so before stating version 3, I need to I need to give you guys an exercise that's useful. Okay, so here's an exercise, and we can discuss this at the end if we have time. But it's pretty straightforward. So okay, so let M prime be a submodule of M and R submodule. Okay, so let M prime prime is equal to M mod M prime. Okay, so I always use the convention that that M prime prime, these always fit in an exact sequence, where the first term is M prime, the second term is a short exact sequence, where the first term is M prime, the second term is M, and the third term is M prime prime. Okay. Okay. So the statement is we have the statement is that M prime prime mod I M prime prime. This is isomorphic to M mod, well, IM plus M prime. So, so quotienting out the quotient by IM is the same thing as quotienting out by IM and the thing that you quotiented out by before. Okay.
And in this example, I is an ideal in M.
Yeah, I is an ideal in R.
An ideal in R.
Yeah, so it doesn't make sense for there to be an ideal in M because M is a module. You can have submodules of modules, right?
Yeah.
But you don't have ideals in modules. And so in general, you don't have multiplication on a module by another module. Yeah, good question. Okay, so let's use this. Let's use this little fact here. Okay, so this is just a general fact about modules, quotients of modules. Okay, so version 3 of Nakayama, and this is where you start to see that it's super important. So version 3 of Nakayama. Okay, so let M be a finitely generated R module. A finitely generated R module. Okay, let I be an ideal. Ideal of R contained in the Jacobson radical. The Jacobson radical. Okay. Okay, so now here's the cool thing. So if M mod IM is generated by some elements in the quotient, so M1 bar, M2 bar, all the way up to Mn bar. Okay, so if I know that these are generators of the quotient, right, then I can lift them to generators. Then M is generated by the lifts of these things. By M1, M2, Mn. Okay, so let me explain the notation here. So here we're using the notation, just kind of, we'll do a little remark over here. So we are using the notation that, if we have M and this can map to the quotient IM, we take M and we map it to M bar. Okay, so we're just using this M bar notation to denote equivalence classes in here. All right. So, but okay. So what this says is that if you have generators, right, of the quotient under this circumstances, that I is an ideal, I is an ideal of R and it's contained in the Jacobson radical, right? Then you can lift the lifts of representatives also generate M. Okay, so let's do a proof. Let's do the proof. Okay, so what we'll do is we're going to apply this thing here. Okay, and so what we want to show is, okay, so what we'll do is we consider the module. Oh. Okay, consider the submodule here, M prime, which is generated by, it's the span of these M1s, or these MIs, right? So this is a submodule of M, right? And what we're going to do is we're going to consider the quotient, right? So let M be M mod M prime, okay? So we want to show that this is 0. To show this is 0. Okay, this would prove. So we're supposing again, as in the statement, that these are generated by this. So we want to show that this module is 0. Okay. So sorry, this is m prime prime. This is a new thing. Okay, so now we're going to apply the version 2 of Nakayama. So we have by version 2 of Nakayama, or by the lemma. Or the exercise, right? The exercise told us that m prime prime mod I m prime prime. Well, this was isomorphic to m mod, and now we just took the coefficients of m plus the thing we quotiented out by to get m prime prime. Okay, but this thing here is 0, and this is because m mod im is generated by m1 bar plus m2 bar plus dot 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 plus or sorry, let's say comma mn bar, right? And this is, I guess, m bar if you wanted to say it, m bar prime. So yeah, so this is part of the hypothesis of the theorem, is that these things generate this. Okay, so all you need to get the whole thing would be if you throw in im, right, and you throw in the m's, right, then that's all of m. Okay, so yeah, so that's what this is saying is, so these are the generators that we had for the quotient, and then this thing gives us all the cosets. Okay. So so that's 0. This quotient here is m prime prime mod I m prime prime. That's 0 by this. So we cook this up so that that's 0. And so now we get to apply Nakayama. So version 2 of Nakayama. This kicks in. And let's just say what it says again. It says m prime prime mod I m prime prime is equal to 0. This implies m prime prime is equal to 0. Right? But what does it mean for m prime prime is equal to 0? Well, since m prime prime, this was m mod m prime, this is equal to 0. Well, this implies that m is equal to m prime. So, in other words, m1, m2, dot, 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 through mn, they generate all of m. All of m. Because that's what m prime was. M prime was this thing. Here. Cool?
I think so.
All right. Yeah, so it tells us that we can lift generators from the quotient. That's pretty cool. Okay. So maybe some more down-to-earth examples? Let's do this in a special example. Like, so what's this Jacobson radical? Okay. So we don't really need to worry about the Jacobson radical so much. I mean, it like 99% of the time when you do this. Okay, so let's do an example. Okay, so let's do some applications. So I have 2 applications for you that I prepared. Okay, so really in this next example, you take your favorite local ring. Okay, so let R be ZP, the p-adic integers. Right, and so remind you that this is a local ring. So let's just kind of remind you that this thing here is a local ring. It's more than a local ring, it's a DVR. It's a complete discrete valuation ring with maximal ideal here generated by P for P of prime, right? So in this case, the Jacobson radical is just the maximal ideal. So in this case, let me go back to the red. The Jacobson radical is just the maximal ideal because there's a unique maximal ideal, okay, for local rings. So you can do this with any local ring. It doesn't really matter. Okay, and so let M be a finitely generated ZP module. Okay, so if V1, V2 through Vn in here are such that their reduction mod P, V1 bar, V2 bar, Vn bar, span M mod PM as a FP vector space. So again, this is a finitely generated thing. So this is a finite dimensional FP vector space. So this thing here is a finite dimensional FP vector space. Okay, and just for clarity, right? Where does this FP come from? This FP comes from the fact that ZP mod its maximal ideal. This is isomorphic to FP, the field with P elements. Oh, I should have made this red, but oh well, this is red. Okay, so so we can reduce the module mod P, and we get some finite set of generators. So this could be a basis for this thing. Okay, so then what Nakayama 3 says, so version 3 of Nakayama says, version 3 of Nakayama says that V1, V2 through Vn generate M. So that's pretty cool. So what you have is, like, if you have any ZP module that's finitely generated, what you can do is you can reduce it mod P. So that gives you a finite dimensional vector space, right? And you can take the basis for that vector space and just lift those to the representatives in the big module, and those will be generators. So you can take, you can find your basis in the good old-fashioned vector spaces and just lift them. Cool? I think that's pretty cool. Okay. Yeah. Feel free to chime in if you have any comments. Yeah.
Yeah, I want to, like, that's way bigger than I thought it was when you were presenting it. So just to be clear, like, these V's generated the module, and then they generate the module, and now they lift from that and generate the, or no, they generate the sub.
I don't know that they're generators of the module to begin with. All we know is that once I reduce them mod P, they're generators of the vector space, right? So it's like,
Sorry, they're associates in the quotient are generators for that, and so they just generate the entire module. Okay, yeah,
exactly. So like you only
Cool.
need to test the generation mod P, right? So
cool.
yeah. So you don't need to know anything about them other than that they generate the module after you reduce the mod P. So it seems like you're losing a ton of information, right? But you're really not, right? That's kind of the weird part, is like you think that reducing mod P might destroy everything, but it doesn't. Okay, so let me give you another example. Okay, Okay, so let M, let's see. So do I want to give you the general one or not the general one? Okay, so okay, so let me give you the general statement, and then we'll see how to prove this general statement in maybe a week or two. Okay, but so let M be a finitely generated R module. Okay, and so let phi from M to M be an endomorphism of R modules.
Taylor, can you briefly say what an endomorphism is again?
It's a morphism of modules from M to itself.
Okay.
That's it. Just like a linear map from M to itself, but R linear.
Okay, yeah.
Yeah, where R is the ring. Okay, so if phi is surjective, this implies phi is injective, or sorry, phi is an isomorphism.
Would you also say automorphism in this case?
Yeah,
or
an automorphism.
that also
Isomorphism / automorphism. An automorphism is just an isomorphism to itself. Yeah. So yeah, this would be an automorphism. So all you need to know is you need to know surjectivity to get an automorphism. Okay, that's pretty cool. And so so you will be able to prove this version. And so let's do the proof in the case where R is a local ring. Is a local ring. Essentially, what this does is the idea is that for module maps you get to check injectivity and surjectivity locally. That's a theorem, right? And so you just localize, and if it's a injective map at every localization, it'll be injective, and if it's a surjective map at every localization, it'll be a surjective map. So it's kind of like a divide and conquer type thing. This is one of these local properties. Okay, so let me go to the proof of this. Yeah, questions?
I was just gonna say, pretty naive, but it seems like surjective from M to itself would already imply automorphism, because otherwise it wouldn't be like well defined or something. But I'm sure there's probably examples otherwise.
Well, like the idea is that if you have a vector space, right? So in the case of vector spaces, if phi is a map from V to V, is an endomorphism of F vector spaces, and phi is surjective, then phi is an automorphism. Okay, that's kind of the generalization of the statement here. And why is this? So let's do the proof idea here is that so this is just the dimension theorem. Right? So the dimension of V is equal to the nullity of phi plus, so this is the dimension of the kernel, plus the rank of phi, right? And so in this case, in this particular application, we're saying that, let's see, so we're saying that this thing, we don't know what this thing is, plus, but we know the rank. The rank is the dimension of V, right? So, well, let me just not do this. Let me just do it correctly.
Yeah, those things. So then if the rank is full or everything, then you're not going to have anything but a trivial null space, right?
Exactly. 0 is the nullity of phi. So you get a trivial null space. But now we're dealing with modules, right? So how do we kind of like extend this thing? So this goes back to this whole thing that I'm like going to reduce mod p, or modulo the maximal ideal, right? And then kind of check the vector space map there, right? So what I'm going to show is that the kernel is 0, right? So I'm going to take the kernel of the map, and then I'm going to reduce it modulo the maximal ideal, and then I'm going to show that that's 0, which shows you that it's 0 to begin with, right? Okay, so that's the idea.
So in vector spaces, you don't have to use Nakayama, and then here we're going to use it.
Exactly. The vector
Or
space is done
reasonable
using
setting.
Nakayama, but we're going to reduce to the vector space case using Nakayama's lemma. Yeah.
That's awesome.
Yeah. So it's like we got to use all our linear algebra, right? Okay. So what we'll do is we'll let M prime be the kernel of phi. Okay, the null space. Okay, so we want to show that this is 0. Is 0. Okay, so let M fracture M be the maximal ideal of R. Okay, so we claim that M prime mod fracture M prime is equal to 0. And so by Nakayama, and once we show this, by version 3 of Nakayama, we'll get M prime is equal to, or version 2, I guess. M prime is equal to fracture M prime. So again, the maximal in the local ring case, the Jacobson radical is just the maximal ideal, right? So this implies that M prime is equal to 0. Okay, and so this shows that so in the kernel being 0 is enough to show injectivity, right? So we were given that it was surjective, and if we get to show that the kernel is 0, then that means it's injective. It's sufficient to check that the kernel is 0 to prove that a map of modules is injective. Okay. Okay. So to do this, to see this, what we'll do is we reduce the map modulo M. We reduce the map modulo M. And there's a very nice functorial way of doing this using tensor products. But for now, you can think about this, and I'll let you guys think about this for a bit. But this makes sense that that you can reduce a map mod M where M bar is equal to M mod MM. That's terrible, right? Sorry, that's so many M's. MM. Okay, so that's what we have here. Okay, so
If you take a subspace of R, like M, excuse me, an ideal of R,
yeah.
and you multiply it by the module, would you ever? And I guess maybe this is all around this discussion. Would you ever lose a basis vector, like cut one off, so to speak?
Yeah, you might lose you could do that. Yeah, that can happen for sure.
It's possible. Okay, so like if that M, the Gothic M was of a certain persuasion or something, then multiplied by capital M, you could cut off some of the bases.
Yeah, but you like, for example, in this theorem here, right here, like you could have junk in here to begin with, right? Where like it wasn't a basis and it just spanned it. That's fine.
Okay, right.
But you don't need to put junk in there, right? So, by this theorem, right, you don't need to include everything. If it's going to reduce mod, if it's going to be 0 mod p, right, then don't even include it, right? Because that's sufficient to generate this as a FP vector space. So you don't need it to begin with.
Yeah, okay.
Yeah. But I mean, you could throw it in there. Yeah, and that's the concern. That is the concern.
It's actually just as a really general question. Beside all this, just like could an ideal times m like lose cut off one of the okay.
Yeah. After you reduce it mod m, yeah. So okay, so we have this thing. So this is reduced mod p. So this thing is a surjective map. This is a surjective map of finite dimensional kappa of m vector spaces. A surjective, I guess, endomorphism of a finite dimensional km vector space. And so let me remind you what km is, right? This is the residue field, right? This is R mod m, the residue field. When you mod out by a maximal ideal, you get a field. Okay? So this is a surjective map of finite dimensional vector spaces, and so by what we said before, the vector space version of this map this phi bar is an automorphism. Okay, in particular, it's injective. Okay, so now we're going to check the lift. So if m prime mod this thing here, m prime was not equal to 0, then any element of this quotient would give a non-trivial element of the kernel of phi bar. Of the kernel of phi bar. But the kernel of phi bar is 0. So this thing. So that's kind of a contradiction, right? So that concludes us. Then that concludes the proof there, right? So we have m prime mod m prime is equal to 0. Okay. All right. And so the general case again. So maybe I should just make a note here for you guys. Is that the general case, right? Without the assumption on R being local, okay, it follows from this fact that that here, this is the map of R modules. So this thing here is so let's do it like this. Phi is surjective, phi is injective, if and only if phi p. So this is the map from MP to NP, surjective for all P in spec R. And this is the same thing, but injective, right? So this is this property that you can check surjectivity and injectivity locally. You can check a lot more things locally. You'll be able to check flatness, integrality, like tons of there's a whole swath of properties that are that such that property of the map holds if and only if it works at every localization. Okay, so I didn't pick out a problem for you guys, and I wasn't sure where you guys were. So I think next class, if it's all right with you guys, I'm going to have you guys do a Grosvenor basis one, and I think I'm going to pick one out from this worksheet, the Cornell worksheet. All right, does that sound okay?
Yeah.
What Cornell worksheet, did you link this somewhere?
Yeah, it's in the thing. It's on the in the problem bank.
Oh, I gotcha.
Right. 59. There's 5 exercises in there.
Cool. All right, thanks.
Yeah.
Thank you.
All right.
Thank
I'll stick around for questions if you guys have any.